So
can you hear us?
yes, I'll just move to the slide. Right. Yeah. So thanks everyone. Yeah. So I first like to thank the organizers for organizing this nice meeting and giving me the opportunity to speak. And I, of course, thank all of you who turned up despite this being a Sunday morning. So, so my plan for the talk is to describe kind of a very active area in probability theory, um, that of this randomly growing interfaces. I'll restrict to one specific class of randomly growing interfaces that has been very thoroughly investigated over the last 20-25 years. And it continues to be a very active area of research. So my plan is to broadly describe some of the main features of this area. Right. So we will talk about randomly growing interfaces, and our interface will be a one-dimensional interface. So that means the interface will be growing in time, which is, so when I say interface growth in 1+1 dimension, it means one space dimension. So the interface is like a curve, a one-dimensional curve, and it is growing in time. By the way, at any point, if you have any questions, please directly interrupt me and ask. So how do we encode this interface? The interface would be encoded by what is called a height function. So height function hxt will denote the interface, the height of the interface at location x at time t. So t starts from 0, and x will be, so we'll be talking about mostly discrete interfaces. So x will be an element of the integer line. Okay, so let us start from very basic. So what is kind of the most elementary such model of a growing interface that you can think about? It's probably the following. So at each location, you increase the height by some random amount, say independent and identically distributed amount, after waiting a random amount of time. So if you are familiar with the Poisson process, so you have this Poisson clock that rings at rate 1, and whenever this clock rings, you increase the height of your column at that particular location by some amount, some random amount. Say, you can consider anything. Let's say you increase it by 1 with probability half and by 2 with probability half, something like that, or any other randomness that you want to take. And let's say that the evolution of the heights of the columns are independent across different locations. So that's kind of the most basic model for this 1+1 dimensional growing interfaces that you can think of. Okay, so it's not actually hard to understand what goes on for this type of model, essentially because of the central limit theorem. So if you look at the height of a column at time t, what exactly is it? It's essentially a sum of IID random variables. And how many are there? Exactly the number of rings up to time t. So the number of rings up to time t is on an average t, because we are ringing at rate 1. It's not exactly t, there will be some fluctuation. It's a random number, but it's essentially t plus some smaller order terms. So you can use a variant of central limit theorem to conclude that this hxt, so the mean will be some constant times t. So the typical value is linearly growing in t. And the fluctuation, so the fluctuation around the mean will be of the order of square root t. And when you scale, so this is exactly the central limit theorem, when you subtract off the mean and divide by the fluctuation, you get, as t goes to infinity, you get a Gaussian random variable. And of course, because I have said that different columns evolve independently, so you'll get this independent Gaussians at different columns. So what is, although it's very simple, so what is important, I would like to point out, is that the nature of this square root t scaling and the Gaussian limit, these do not depend on the microscopic features of the model, in the sense that it does not matter whether you chose to increase your heights by 1 or 2 with probability half. It would be the same if you would have chosen like 1 with probability 1/3, 2 with probability 1/3, 3 with probability 1/3, or any other reasonable random variable, as long as central limit theorem can be applied. So this is a very important feature in probability, which is often referred to as the universality. So the universality means that the large scale behavior of the model depends on some broad characteristics, but not on the microscopic details. So here Gaussian nature kind of depends on the fact that the increments were IID, but it does not depend on the exact distribution of the increments. Okay, so this is often this is one of the examples of the Gaussian universality class, which is the most ubiquitous universality class there is in probability. But also you can see that this model is a bit too simple, right? I mean, this doesn't really capture any kind of nice interaction between different locations, which you would expect in any model of interface, which is supposed to model some real naturally occurring phenomenon. So this Gaussian universality class does not really cover all interesting class of randomly growing interfaces. So there is so there are a large class of growth processes which exhibit a different universal behavior, and they are also more so they also mimic the behavior of many interesting natural growth processes. So these can be classified by like 4 basic properties. The first 2 is already present in the previous toy model we described, which is that the growth is local, so there is no long range interaction. So in the previous model, there was no interaction at all. And the growth is independent across space and time. So that was also there in the previous model, because at each space-time location, whether or not there is a ring and how much the height increases, that's different. That's independent across the location of space and time. But the 2 additional features which make this class more interesting is the following. So one is that the growth will actually depend non-linearly on the slope of the interface. And the final one, which is referred to as a relaxation mechanism, which essentially means that whenever in the interface there are peaks and valleys, right? So whenever there is a valley, the height increase at the valley will be larger than the height increase at the peak. So the valleys are filled quickly. So this is called a relaxation mechanism. So adding these 2 extra features kind of lets you include many more interesting processes of random interface. And the universal behavior that is expected in this situation is widely different. So first of all, the fluctuation. So in the the typical value, the interface will still grow linearly. At time t, the typical value will still be of order t. But the fluctuations now becomes much smaller than square root t. So these are subdiffusive fluctuations, and the scaling limits becomes non-Gaussian. So it's very different. Okay, so are there any questions so far? All right. So if not, let me tell you a little more about this particular class of interfaces. So in some sense, this story starts although there are studies of these kinds of models going back to the 60s. So essentially, I mean, the main act of the story starts in 1986, where these 3 physicists, Kardar, Parikh, and Zhang, they came up with a way to describe the large behavior. Yeah, was the question? Was there a question?
No.
Okay. So they came up with a way to predict large-scale behavior of this class of models. So, I don't know if you are not from this area, you might not have heard of Carter and Jung, but you probably all have heard of Parisi because he was awarded the Nobel Prize in Physics last year. So these three people, so this is a screenshot of their first page of their paper from PRL in 1986, which is called Dynamic Scaling of Growing Interfaces. And I'm not exaggerating if I'm saying that this is one of the most influential paper in statistical mechanics as well as probability theory over the last 35, 40 years. So what did they do in this paper? So they postulated a differential equation, which they said would capture the large-scale behavior of all of the models that satisfy those four general features. So what is this equation, which is now referred to as the KPZ equation? So they wrote this equation in the higher space dimension also, but I'll only stick to the 1 plus 1 dimension case. So what is this equation? So this is the del H del T, which is which represents the rate of growth of height function in time. So this is equal to, so there is a Laplacian term. So we have this del 2h del x2. So this is the relaxation mechanism. This represents the relaxation mechanism I was talking about. And then there is this nonlinear slope dependent term. So you have this del h del x whole square. And then you have the randomness. So there is this psi xt, which is a random quantity, which is the space-time white noise. Okay, so this is a partial differential equation, but there is a stochastic a random term here. So these equations are called stochastic partial differential equations, in short SPDs. So they postulated that this equation will govern the large-scale behavior of all of those models. Okay, any questions? Okay, so the problem with this is that there is this nonlinear term. There is this del h del x square term, which makes this equation ill-posed. So to mathematically develop a theory of solution for this equation was extremely difficult, and it was actually it was part of Martin Harar's Fields metal winning works, which was developed like 10 years or so ago. So the theory of solution of this KPZ equation was developed rather recently. But much before that, so when in this KPZ paper, what they did is that they did a non-rigorous what is called a renormalization group analysis of this equation, and predicted that models in this satisfying, this models whose large-scale behavior is governed by this equation, they'll have the following features. So they said that the fluctuation, so at time t, the fluctuation of the height, instead of being t to the half, now will become t to the 1/3, and there will be a correlation length which is given by the exponent 2/3. So what do I mean by that? It means that if I look at the interface at time t, and if I look at two spatial location x1 and x2, which are much further away than t to the 2/3. So if x1 minus x2 is much larger than t to the 2/3, then the correlation between the heights is very small. Whereas if they are much smaller than t to the 2/3, then the correlation is very close to 1. So only at the scale t to the 2/3 do you see a non-trivial correlation. So this is the way when physicists refer this type of phenomenon by saying like the correlation length is t to the 2/3. The correlation length exponent is 2/3. So that's what it means. So there are many examples of such models which it's believed that they are governed by this type of behavior. I'll explain some of these models later on. But before that, let me tell you why this particular equation and this type of models have drawn so much attention even outside mathematics. It is because in many natural experiments, you actually see these type of features popping out. So this is a picture from a paper in 1997 where they were actually growing bacterial colonies in a petri dish, and if you look at the interface, if you look at the boundary of the colony, this picture to the right, so you will see this kind of 1/3 and 2/3 behavior. So that's one example. So the second example is another PRL paper from 1997, where they were experimenting with slow combustion of paper. So you are burning a piece of paper slowly, and you see the jagged edges that are formed by the fire. So there also apparently you see this type of KPZ scaling. This is a picture about interface between dynamic scattering modes. So this is something in, I guess, crystallography. So there also there are two different types of scattering modes, and the interface between them, it seems like they also satisfy similar things. And the final one is it's an example that appeared in Nature about 10 years ago. It's like when you spill a drop of coffee on a piece of paper and let it dry. So these dried drops, they will not be exactly a sphere, right? So there will be some, they'll have some shape, and there will be some sort of fractal protrusion around this main shape. So what this paper kind of investigated was that if your coffee contains spherical bits, then they will have a certain kind of growth, which is not the KPZ growth. But if it contains ellipsoidal colloidal particles, then when you actually let this coffee drops dry, then the boundary of your dried coffee drops will look like this, this type of KPZ predicted interface. So there are many more examples. If you search in Google saying like KPZ in real world or something like that, you see many other examples. So anyway, so I just wanted to show you some of these pretty pictures because I because they're pretty, first of all, and then I also wanted to convince you that this is actually, even if you don't care about the mathematics, this particular phenomenon is actually of interest in many other fields also. All right, so let's go back to the maths. So what we're going to do is we're going to, of course, all these very complicated mechanisms, we don't really have any way to model them in a tractable manner. So we're going to stick to much more simplified models of random interface growth. So one of these models, which we'll pretty much stick to for the rest of the talk, is called the corner growth model. So what exactly is a corner growth model? So you can start with different initial conditions, but I'll stick to this wedge initial condition. So this is my interface at time 0. And then how does the interface grow? It grows by flipping corners. So whenever you have a corner like this, whenever you have a V-shaped corner like this, after waiting a random amount of time, you flip it to a lambda. And then you again start flipping the remaining corners. So how does that look like? So of course, at start, you have only one corner. And then after some random amount of time, you have grown. So this is the corner, this is the shape you now have. So now there are two corners, right? So now you have this W-shaped thing. So there are two corners, each of which can presumably flip. So each of which, so after this, after the shape becomes this, each of these two corners start their own clock. And maybe the right one rings first. So now you have this. Again, you have two corners. You have their clocks. Maybe now the left one rings. And now you have three corners. And then each of them have their own clocks. And that's how you grow the interface. And so how does it look like in large time? It looks something like this. So the height will be some constant times t. So in particular, in this case, it will be t over 4. It's not important what that constant is. But what is important is that around this mean value, you have this fluctuation of t to the 1/3, and in space, you have the scaling of t to the 2/3. So this was the correlation length I was talking about. And if you map this t to the 1/3 times t to the 2/3 size rectangle into a unit square, what you will see is a non-trivial stochastic process. So that's what the prediction is. I mean, in this case, it's actually no, but that's what the general picture is for models in this class. Okay. Yeah. So any questions before I move on further? Any questions about the model so far? Okay. So what I'll do is that we will not directly study this corner growth model. We'll study reparameterization of this model, which is somewhat easier to which is I find it somewhat easier to study this version, which is called the last passage percolation on Z2. So essentially, you should think about the last passage percolation model as the corner growth model rotated 45 degrees clockwise. So I had this V shape. Now I rotate it 45 degrees clockwise, and then I get this picture of the first quadrant, and these numbers, so they are independent and identically distributed. So in each cell, I put an independent and identically distributed exponential random variables. So you should think of these random variables as the time you have to wait before that particular corner is flipped. So you have this x11. So after waiting x11 amount of time, you flip this corner. So you kind of mark this cell as occupied. And then you have these two corners. Each of them have their waiting times x12 and x21. You flip those corners or you mark those cells as occupied after waiting that amount of time. So that's how you correspond this picture of IID weights on the lattice with the picture of the growing interface in the previous slide. Now, what do we study in this model? We study the following statistic, which is called the last passage time. So what is the last passage time? So you fix two vertices, u and v. So let's say u is this 1, 1 and v is this ij. And then what do? You take any upright path. So these u and v, they're going to be coordinate-wise ordered. So we're going to only define last passage time between two coordinate-wise ordered points. Then what do? You take a path, so call that path pi, going from 1, 1 to ij or u to v, if you want. Then you sum the random variables on that path. So you sum, this is x, w, w and pi. So that gives you the weight of that path. And then you maximize that weight over all possible paths, starting at u and ending at v, all possible upright paths. So this maximum is what is called the last passage time between u and v. And how does it connect to the picture in the previous slide? It's actually not hard to check. I'm not going to do that check, but it's actually easy to check that in the previous picture. So let's just describe in so this 1, 1 to ij, or say 1, 1 to ii. So let's say that I'm looking at the passage time from 1, 1 to ii. So the last passage time from 1, 1 to ii is exactly the time it takes for the height at 0 to become I. So the correspondence between this last passage percolation picture and the corner growth model before is that the last passage time gives you the time it takes for a height at a certain location to become a certain value. So in particular, if you look at the passage time from 1, 1 to I, I, it will be the time height at column 0 to become I. So in particular, so you should think about these diagonal lines. They represent the location. So the diagonal line x equal to y represents the location 0. The diagonal line x equal to y plus 1 represents the location 1, and so forth. And the anti-diagonal lines, they represent time. So the anti-diagonal line passing through n, n, that you should think of as something like time n. Okay, so the diagonal direction is the time direction, and the anti-diagonal direction is the space direction. That's how you should think about this picture. So again, you can easily see that by flipping it back. So rotate this picture back 45 degrees counterclockwise, and you'll see that the anti-diagonal direction is aligned with the space direction and the diagonal direction is aligned with the time direction. So one other object that will be of interest to us is the optimizing paths. So because the exponential random variables are continuous, there will be an optimum, a unique optimal path which will attain this maximum, and that path will be called, we'll call it a geodesic. So notice that this is not a metric. This is like an anti-metric. So it satisfies the reverse triangle inequality. So, because I'm taking the maximum, so going from X to Y to Z is actually worse than going from X to Z directly. So it's the it satisfies the reverse triangle inequality, and it's an anti-metric rather than a metric, but we'll call the optimizing path the geodesic anyway, because it locally optimizes the distance, so to say. Right. So the reason I chose it to be exponential here is because the exponential weights make the growth of the interface in the corner growth model Markovian. Because of the memoryless property of the exponential distribution, the growth process corresponding to this class passage percolation field will be a Markov process, and that makes analysis of this model actually in some sense more tractable. So as I said, it's believed, so I'll come back to this later. So there should not be anything special about exponential except that it makes the analysis possible. So what is known about this model is, so a lot of things are known. So in particular, as I said, the growth is linear. So in particular, if you grow, so look at the picture on the right hand side. It's so the blue region that represents the set of vertices that have passage time less than equal to t from the origin. Okay, so a vertex is marked blue if so there is some large t. So the vertex is marked marked blue if the passage time from origin to that vertex is less than equal to t. So this boundary of this blue region, that exactly is your interface. And the interface, as you can see, so it has a limiting shape and there is some fluctuation around it. So the limiting shape can actually be obtained explicitly in this case. So one can show that if you're going in direction x comma y, your speed is of course linear, but after you scale by the speed, you get this shape square root x plus square root y whole square. So in particular, if you put x equal to y equal to 1, you're going in the diagonal direction, your speed is 4. And then, as I was saying, the fluctuation exponent 1/3, that's also known rigorously in this case. So if you subtract off the typical value, which is 4n, and you divide by n to the 1/3, so there is a scaling constant 2 to the 4/3, which is not important for us. Then this height, this, centered and scaled height, converges weakly to a non-trivial distribution, which is called the GUE Tracehuidum distribution, which will be familiar to you if you're familiar with random matrix theory. So this GUE Tracehuidum distribution occurs, as the scaling limit of the largest eigenvalue in many random matrix ensembles. And so this 2/3 exponent, as I have already mentioned, it occurs as a scaling scaling exponent for correlation length. So how do you see this 2/3 exponent in the last passage percolation picture? So in the last passage percolation picture, one way to see this 2/3 exponent is to look at the geodesic. So you look at the geodesic from, say, the origin to the point n comma n, and you ask, how far does this random geodesic go from the straight line joining the 2 points? So from the diagonal. So the answer to that question is that the typical fluctuation of this geodesic around the diagonal is of the order of n to the 2/3. So that's how this 2/3 exponent pops up in the last passage percolation picture. It also, there are many other ways you can see this 2/3 exponent in the last passage percolation picture, but this is one of the more geometric ways to see it. Okay, so as I said, physicists will tell you that this model, this behaviors, they're supposed to be universal. So what do I mean by universal? So this constant 4, it's not universal. It depends on the model. This constant 2 to the 4/3, it depends on the model. But the behavior that you have after you scale by the first order linear term, after you center by the first order linear term and scale by some constant times n to the 1/3, so the scaling is of the order of n to the 1/3 and the limit is FGE. These two facts are supposed to be universal. Okay. So under very mild conditions, so we have assumed exponential, but under very mild condition, some sufficiently fast tail decay and something like that. So under these very mild conditions, you believe that you see this scaling and this limit. But unfortunately, we are still quite far from understanding the universal behaviors. What is rigorously known, so these things are rigorously known only for a handful of models. So including the exponential LPP models, also the geometric last passage percolation model. And there are a couple of other models. So in particular, you can consider this model in continuum called Poissonian last passage percolation, which is a variant of this longest increasing subsequence problem from combinatorics for a uniform random permutation. And then there is this semi-discrete model where your randomness lives on lines indexed by the integer line. So it's like R cross Z. So your randomness is a family of Brownian motions indexed by Z essentially. So and then you do your last passage percolation on that picture. So this is called a Brownian last passage percolation. So these are the handful of models for which this prediction is rigorously verified. These models and the reason we can do this rigorous analysis for these models is because there are some remarkable bijections. I'll tell you a little bit about those bijections in the next slide. But there are some remarkable bijections which lets you write down explicitly the formula for the last passage time. So these are therefore referred to as exactly solvable models. So there are some like almost magical bijections which you can exploit to write down the density for the last passage time explicitly. So much of the KPZ literature over the last 20 years, at least on the discrete side of things, is studying these, identifying these exactly solvable models, studying these formulas, and doing hard analysis on these formulas, take appropriate limits to establish these predictions in those specific cases, right? So yeah, so maybe I should stop at this point and ask if there are some questions, because I will now move on to describe some of the highlights of this area over the last 20-25 years. So any questions about the general model and the general features?
Yeah, just one quick question. So the h of x comma t that you defined in the beginning is a discrete function, right? It takes values. So the KPZ model assumes some sort of regularity for the function h of x comma t. So is that a limitation, or
so if you want to rigorously prove that any of these models converge to the KPZ equation, you have to scale. You cannot do it at the level of discrete functions, right? So you have to scale it. So that's how it is done. So if you want to actually have a rigorous result showing that some of this model converges to the KPZ equation, you have to scale it properly. So they will not be at the level of functions on Z. So they will become functions on real line after appropriate scaling, and you sort of interpolate these functions, and after this sort of scaling, it becomes a function on the real line, and then it converges to the DPZ equation. Actually, this so one should not directly think of as these last passage percolation models converting to the KPZ equation, because I mean, the last passage percolation models actually are zero temperature analogs of polymer models, where so the KPZ equation should be thought of as the scaling limit of positive temperature versions of this last passage percolation model. So KPZ, this last passage percolation models, after taking appropriate scaling, it converges to something that is called the KPZ fixed point. And then in another appropriate limit, this KPZ fixed point, so KPZ equation should also convert to the KPZ fixed point. So this is kind of.
Yeah, so the only reason I was asking that was, do you assume any continuity of h of x comma x and h of x comma t?
So if you are thinking of it as a function on Z, it will not be continuous, right? So there will be some jump.
To KPZ.
But once you scale, so suppose you scale this, so you scale this function. So on the interval of an interval of length n kind of becomes an interval of length 1, and you scale the value of the function also according to this n to the 1/3 scaling, then it does not become continuous, of course, because then you will be defined on like 1/n lattice, right? But you can interpolate it. So if you actually want to get convergence at the level of functions, you will have to make it reside in the same space, right? So you'll have to make it continuous by doing some interpolation or something like that.
Okay.
So if you want to have convergence, so I'll come to such a result in a couple of slides.
Okay. Thank you.
Where you will see that this convergence will happen after scaling, and after you have made sure that they reside in the same function space.
Okay.
So you have to do so. It's like saying that random walk converges to Brownian motion, if you are familiar with this type of statements, right? So random walk essentially is a discrete object, but when you say random walk converges to Brownian motion, you kind of add these, you kind of add those by lines, so you make it a continuous object that also lives in the function space C01 or something like that, and then you talk about convergence of random walk to Brownian motion, right? So it's essentially something similar. So you can talk about convergence only after you have made things in the same reside in the same function space. But after you have scaled, it will not have like very large jumps. So you can actually make that precise in certain settings. I'm not sure if I answered your question. But,
no, you did.
All right. So any other questions? No. Okay. So let's move on and talk a little bit about some of the highlights of this world. So sometimes I have seen people refer to this explosion of results that has happened in this area starting 1999 or around. So it's a KPZ revolution, and it's still kind of going on. So let me. So of course, this is such a huge literature. I cannot even possibly cover 10% of all the interesting things. So what I will try to do is I'll try to restrict myself to the specific last passage percolation model. So I should mention that last passage percolation is not nearly the only model in this KPZ world. There are many other models, but last passage percolation is one of the canonical zero temperature models, as I said. So what I'll describe over the next couple of slides is that some of the main results in the last passage percolation world in the last 20-25 years. So the story starts, at least as far as the rigorous mathematics is concerned, by the seminal paper by Jinho Baik, Percy Type, and Kurt Johansson in 1999, where they obtained this n to the 1/3 fluctuation and this Tracy-William limit for the Poissonian last passage population. So as I said, this Poissonian last passage population, you can think of it as the longest increasing subsequence problem in the uniformly random permutation. And the key of the analysis is actually the well-known RSK or Robinson-Shenstedt-Knuth correspondence, which maps permutations to Young tableaus. So what one can do is that one can use this RSK correspondence and the fact that the length of the longest increasing subsequence is kind of the length of the first row of the corresponding Young tableau. You use that fact and you use these hook length formulas. So there are connections to representation theory and algebraic combinatorics, which you use to write down explicitly the distribution of the length of the first row of the Young tableau corresponding to a uniform random permutation. It's a complicated formula, but you can write down the formula nonetheless. So that's what this paper of Bike-Type and Johansson did. So they wrote down the formula and they analyzed the formula. They got this n to the 1/3 fluctuation and the Tracy-William limit. Soon after, Johansson did the same thing for exponential and geometric last passage population. There also the main observation is this bijection. So they, in the exponential last passage population setting or the geometric last passage population setting, you don't use the standard Robinson-Shenstedt-Knuth correspondence. You use what is known as the geometric RSK correspondence. Using that, you can nonetheless write down this formula for the density of, say, T of 0, n. The 0, n means the passage time from the origin to the point n, n. Now here is what something magical happens. So after you write down the density, you see that the density is actually the same as the density for the largest eigenvalue of a very interesting random matrix ensemble, which is called the Laguerre unitary ensemble, often referred to as LUE. So this is, if you're familiar, so these are eigenvalues of a complex U-chart matrix with Gaussian, standard Gaussian entries. The useful thing about, so there are many, so once you have obtained this correspondence with this random matrix ensemble, which again is almost magical, we had no way to actually see that it will be this random matrix largest eigenvalue of the random matrix, or at least I don't know of any way to predict without writing the explicit formula. But once you have done it, there are many ways to exploit random matrix theory to proceed from there. One particular way is to note that the eigenvalues of these V-chart matrices, so these points on this Laguerre unitary ensemble, they form what is called a determinantal point process, which means that the multi-point functions of this point processes are given by some determinants. And using this fact, one can actually write down the distribution function of this last passage time as a Freedom determinant. So you have some kernel Kn, and you write down the distribution function as some Freedom determinant when you think of this I minus Kn as an operator operating on L2 of, say, S up to infinity. Okay. So this formula is very complicated, but people have developed tools for asymptotic analysis of this kind of formulas for a very long time. So in particular, you can use steepest descent methods or like this Riemann-Hilbert approach, this kind of thing. So once you have this type of Freedom determinant formulas, there are ways in analysis that people have developed over long years to actually analyze asymptotic behavior of this formula, and that's exactly what Johansson did. It's hard analysis, but it's possible. And once you do the analysis, you will see that this Tracy-William distribution, which I have not said what it is, but it is related to the Painlev-2 equation. So solution, yeah, again, this is not really something I know much about, but so you have this equation called the PD called Painlev-2 equation, and then you have a solution whose asymptotics are given by the Airy function. And when you do the asymptotic analysis of this Freedom determinant, you get formulas that are coming from those parts of analysis. So at the end, you get a distribution which matches this Tracy-Widom distribution for from the random matrix theory. So here is the sort of the relevant result which answers the question from a few minutes ago. So about convergence to some continuous processes. So this is, so think about so I said this 1/3 and 2/3 scaling, right? So now what I'm going to do is this, I'm going to look at a large time n, and I'm going to scale the process. So I'm going to scale the process in space by this scaling factor n to the 2/3. So in particular, I define t and u. So u is a real number. So t and u I'll define as the passage time from the origin to the point n plus u times 2n to the 2/3, comma n minus u times 2n to the 2/3. Now you'll point out immediately that u times 2n to the 2/3 need not be an integer. I will just take the integer part. I can do any kind of approximation, but I'll do the integer part. So this lets me define a real valued function, which will not be continuous, but it will have actually some jumps, because depending on how I need to do this, how I do this kind of rounding. But what one can do is that one can show that if you look at this t and u, you center this by 4n, which is the typical value at u equal to 0, and you divide by the scaling constant 2 to the 4/3 times n to the 1/3. And then in terms of finite dimensional distributions, it converges to a continuous stochastic process. So which is, I have written, it's like, so remember that there is, so look at this picture. You have something that is stationary, but it is growing like parabolic as a parabola near the ends. So when you have moved from the corner growth picture to the last passage picture, last passage population picture, it's essentially an inversion. So this parabola, the parabola that was being added will now be subtracted, and so that is some deterministic subtraction. And then there is a stochastic process, stationary stochastic process, which is called the Airy-2 process. So this convergence is a priori in terms of finite dimensional distribution. So if I take like u1, u2, un, then I get that t and u1 minus this, t and u2 minus this, and so on. They converge in distribution to a2. So this a2 of u1 minus u1 square, a2 of u2 minus u2 square, and so on. But once you have made, once you have appropriately rounded things so that a2 now actually lives in say C of R, then you can actually upgrade this to the weak convergence also. So weak convergence in the space of all continuous functions in the on R, say, or on some compact subsets of R. So this is the kind of convergence that I was talking about. So you have to, so a priori you get some kind of finite dimensional convergence, but once you have made things smooth enough, so all the functions are kind of in nice enough spaces, then you get also the weak convergence to some continuous stochastic process. So this was, in a physics literature, it was done by Professor and Spahn in 2002, and then Borodin and Ferrari did it in 2008. I mean, they did much more, also many other variants of this. And so this was for the wedge initial condition, and you have similar formula for some other initial conditions also, like if you start with the flat initial condition, so just a flat substrate rather than this V-shaped substrate, then you get some other stationary stochastic process which is called the Airy-1 process. So the reason these processes are called Airy-1 or Airy-2, something like that, because their multi-point distributions are given by some kernels which involve Airy functions. Okay, so that's yeah. So there are other formulas. Yeah, was there a question?
No.
Okay, right. So this is kind of where we are at. So how much longer do I have actually?
Around 10 minutes, 10 to
Okay.
15 minutes.
Okay, great. Yeah. So anyway, so these are so this is the convergence of a process. So convergence of the profile at some large time as time goes to infinity. And then you can also ask about what happens to if I scale instead of fixing a time and scaling the space, if I jointly scale the time and space. So then you get again a random field, which is nowadays referred to as a directed landscape. This was first constructed only recently by in this work of Under One, Janusz Schwartzman, and Van Viral. So they started with this Brownian LP model and constructed this scaling limit. Very recently, they have also constructed it starting from other exactly solvable models. So these are some of the highlights of this integrable side of things in the last 20 years or so. But what I wanted to describe in the last 10 minutes of the talk is a more geometric approach. So rather than relying only on this exact formula and their analysis, what one so recently people have also started looking at more combining this exact formula with more geometric approach, mainly via understanding of the geometry of the geodesics. So for these models that are not exactly solvable, essentially you only have those geometric approach, and it has given rise to a limited success in the study of those non-integrable models. But the key observation is that because you have this exact formula and some estimates coming from this, you can actually use that as ingredients to get better understanding of the geometry of the geodesics. And in turn, you can use those better understanding of the geometry of the geodesics to say more about the underlying landscape that are not the information you can get by combining these two is sometimes more than you could directly get from analyzing these exact formula. So this is an approach which people have been pursuing over the last 5-10 years, maybe a little less than that, and it's also the part of the story where I am personally involved in. Um, so I'll tell you in the next 5 minutes or so some of the flavor of the kind of results that you can expect when you are studying this the geometry of the geodesics, and at the end I'll also tell you some of the application of this geometric approaches where it has been successful in understanding things which could not be understood by analyzing the exact formula directly. So one of the first things you can ask about the geometry of the geodesics is what I said. How far does the geodesic stray away from the straight line? So as I said before, so this is given by so let's consider the geodesic between the origin and the n comma n. So let's TFN. TF stands for transversal fluctuation, which it denotes the maximum distance from the geodesic and the diagonal. Okay, so now, so as I said, this typical value of this transversal fluctuation is like n to the 2/3, and one can actually get quite precise scale estimates for that. So in particular, we showed that the transversal fluctuation being larger than some large constant times n to the 2/3 decays like e to the minus k cube. So if there's some large constant k, you get the decay e to the minus a constant times k cube. So there was this. There is also corresponding lower bound, which was proved by this Alan Hammond and paper by Alan Hammond and Schroeder. So that's one example of a result about the geometry of the geodesic. And you can also ask. So this is about large k, and you can also ask the opposite question, like what is the probability that the geodesic actually does not deviate that much from the diagonal? What is the probability that the geodesic always stays within a delta wall at the scale n to the 2/3 of the diagonal? So if you're familiar, with so this is exactly the analog of the question that you asked. So the small wall probability of a Brownian motion. So what is the probability that the Brownian motion stays within a small t? So it's kind of the analog of that question for these geodesics. And here we showed that that probability decays something like e to the minus 1 over delta to the 3/2. So again, comparing with Brownian motion, there you'll get e to the minus 1 over delta square. So this exponent 2 gets replaced by exponent 3/2 here. So these are kind of some of the results you can obtain while studying the geometry of the geodesic. There are many more which I don't want to go into, but here are some of the examples. So you can, for example, estimate. So if you have geodesics starting at different points but going in the same direction, you can estimate how long does it take for them to merge. You can ask, in a certain patch of space, how likely is it that there are many disjoint geodesics? See, because it's a random environment, all the geodesics will tend to pick good locations to pass through, right? So you actually expect most of the geodesic to merge with one another. So one can make actually quantitative estimates saying how rare is it to actually see a lot of disjoint geodesics in an area. So there are a number of such results about the geometry of the geodesics that you can obtain. And finally, using this, as I said, so using this information about the geometry of the geodesic, you can get information about the underlying landscape which were not directly accessible via the analysis of the exact formula. So in particular, some examples are like you can study this exponential LPP with a defect line. So kind of you can speed up or slow down the speed at which the interface is growing at one particular location. So you introduce a defect. So for that kind of defect, you can use the understanding of the geometry of the geodesics to understand the behavior of the defective model. And then you can ask like what happens to the correlation. So if I look at the interface growing in time, and if I ask what is the correlation between the interface at time t and interface at time t prime, when t and t prime are either close or very far away, you want to understand the asymptotic behavior of the correlation decay. That question one can also answer by using this leveraging this understanding of the geodesic. And then there are other things like fractal. So you want to understand fractal properties of the underlying landscape, or there are particle systems associated with the LPP model, and you want to understand the mixing properties of such particle systems. Those are also the questions where understanding of this geometry of this geodesics has come in handy, as you can see. So these are so there are many recent works, some of which I have been involved in, some of which by my co-authors, and there are other people also working in this area who have exploited this understanding of the geometry of the geodesics to some extent to give new information about the landscape which previously were not accessible just by looking at the exact formula. So to end, let me summarize by saying that I hope that I have convinced you that this topic of KP's universality it's an important phenomenon in statistical physics and many other real world problems, but it has been quite mathematically challenging to understand. So one studies these models to get some insight, one of which is planar exponential LPP. And then, so there are these two approaches. One is using the exact formula and hard analysis on that. And the other one is to look at more percolation-like techniques, geometric techniques in understanding the geometry of geodesics. And if you can combine these two, they can often feed into one another and give more information. So that's kind of an avenue of research that is being pursued now, and it is some limited success to report. All right, so but we are still very far away from understanding the real big questions in this area, which is the question of universality, to extend this type of analysis to non-integrable models. So just to give you an example of a non-integrable model, we consider the first passage percolation, where you have you put IID weights on the edges of the lattice, and instead of maximum weight, you kind of look at the minimum weight of a path into vertices. Physicists will tell you maximum, minimum, it's all the same, it's all universal, there's nothing different. The behavior is no different than it was in LPP. Well, numerically, that seems to be correct, but there's almost no rigorous evidence. So this is a picture of a first passage percolation model where you have looked at the set of all vertices which have passage time less than equal to t from the origin. So this is what it looks like. There's a limit shape, and the fluctuation around that limit shape is of the order of n to the 1/3, where n is the radius. But no, there is no rigorous evidence. There are almost no rigorous evidence. I mean, the best thing you know is that the fluctuation is at least like square root log n, and at most like square root n over log n, something like that. So it's very far from the predicted value of n to the 1/3. So these understanding these type of models where you do not have any integrable structure remains a major challenge. All right, so I'll stop here, and thank you very much for the attention, and yeah, I'm happy to take questions. Okay.
Let's take questions from the audience. There any questions? If not, let's move over to the online audience. Please unmute yourselves and ask the question if you're having.
Yeah, one quick question.
Yeah.
Do you think are there any ergodic theories being used to address this first percolation model?
Sorry, can you repeat again?
I asked, are there ergodic theoretic tools used to address this first percolation model? That's what I wanted.
Can you? I can't hear you clearly. Can you please repeat what kind of in the first passage percolation model? What do you want to ask?
Ergodic theoretic tools.
Yes. So actually, there are actually very interesting connections with ergodic theory when you are talking about this first passage percolation model, because so as I did not explain, so these processes are what are called the subadditive processes. So to establish the first order behavior, you use this Kingman's subadditive ergodic theorem. So one can actually extend this process. So I have restricted to this IID environment, but one can actually extend much of this analysis, or at least the first order analysis, to general stationary ergodic environment. And so one can actually so in the first passage percolation, in the non-exactly solvable cases, one often resorts to these ergodic theoretic methods to give some information, because there are no exact formula there. So so to make any progress, you actually have to use some other means to get this to track the behavior of the joint behavior of the first passage time. So there are some ergodic theoretic techniques that have indeed been useful, but
So,
with those ergodic theoretic techniques, you cannot, I mean, at least in the current state of things, you can't really hope to get the precise exponent. So you can get some information, but it seems hard to use those ergodic theoretic techniques to get like the n to the 1/3 fluctuations and things like that. So the application of ergodic theoretic ideas have given to some results, some improvements, but they seem still quite far from actually getting the optimal results.
So what I was interested in asking was, so what is usually considered as the transformation function here? Is
So
it
it's the translation. So the translations of the lattice.
Okay.
So under the translation, so if you have an IID environment, of course it is ergodic under the translations, but you can consider more general ergodic environments that are ergodic under translations, and you can prove most of the basic results under that sort of weak assumptions.
Okay.
Questions from the online audience? There don't seem to be any more questions.